Welcome to the Walton Pi. Today we're going to be talking about improper integrals. So improper integrals are integrals where the domain of the integration is not well behaved in a sense. So for example, in standard definite integrals, we are integrating over a closed interval from a to b, where both a and b are finite and the function is continuous on the entire interval. An improper integral is where one of these things breaks. So one of those two conditions are going to be violated. So what that means is our first type is we could have one or both of our bounds be infinite. So those are going to be improper integrals. They don't match what we want them to look like when we are looking at a definite integral. So they might look like the integral from a to infinity of a function, or maybe they'll be the integral from negative infinity to a value b of a function, or maybe they'll be the integral from negative infinity to infinity. All three of those are possibilities where we might have infinite bounds on our integral. All of these are considered improper integrals. So the definition for these integrals is as follows. So if the integral from a to t of f of x dx exists for every t bigger than x, then the integral from a to infinity of f of x is equal to the limit as t goes to infinity of the integral from a to t of f of x. So assuming this limit exists and is a finite number, we say that this is a convergent improper integral, and it'll converge to whatever that number is. And so that's the value of the improper integral. If the limit does not exist, though, we say that the integral is divergent. A very similar definition happens for our second type of improper integral, where we have the integral from negative infinity to b. That's just going to be the limit as t goes to negative infinity of the integral from t to b of f of x dx. If both the integral from a to t and the integral from t to b exist for all t's, then we can define the integral from negative infinity to infinity of f of x dx as the integral from negative infinity to c of f of x dx plus the integral from c to infinity of f of x dx, where c is able to be any real number. That is how we would define this one. For some types of integrals, there are easy ways to tell if it'll converge or diverge. So the integral from 1 to infinity of 1 over x to the p, this will always converge if p is bigger than 1, and it will always diverge if p is less than or equal to 1. So that is a useful thing to know anytime you're trying to determine if the integral of 1 over x to the p, if that's going to converge or diverge. You can just look at the power of p and be able to tell. So this is what's called the integral p-test. You'll talk about the p-test again when we are talking about series, and then there is a summation p-test. So we'll be able to be talking about that later on. Our second type of an improper integral is when there are discontinuities in the domain of the function. So we might have a discontinuity at an endpoint, or we might have a discontinuity somewhere in the middle of the function, or in the middle of our interval. And so those discontinuities are other places we are going to have to deal with when we are trying to figure out if this integral is convergent or divergent. So the way that we would define it here is if our function is continuous on the interval from a to b where it includes a and discontinuous at b, then we would say that the integral from a to b of f of x dx is equal to the limit as t goes to b from the left of the integral from a to t of f of x dx, assuming that the limit exists and is finite. The reason we have to approach b from the left is we have to stay in our interval. So we can't approach it from the right because that would be outside our interval. So we are approaching b from the left. If it is instead discontinuous at a, we would take the limit as t goes to a from the right of the integral from t to b of f of x dx. So that again is just so it stays inside the interval. We could also have a discontinuity somewhere in between a and b, and so then we would say it's the integral from a to b of f of x dx equals the integral from a to c of f of x dx plus the integral from c to b of f of x dx, assuming that the two new integrals are both finite in which case that's how we would compute that. So we've transformed this into two integrals where there's discontinuities at the endpoints rather than somewhere in the middle. So remember we had our integral p-test when we were doing the integral from 1 to infinity of 1 over x to the p. That converges if p is bigger than 1 and diverges if p is less than or equal to 1. There's a similar test for integrals beginning at 0. The integral from 0 to 1 of 1 over x to p, that will diverge if p is greater than or equal to 1, and it'll converge if p is less than 1. So notice both cases have it diverge when p is equal to 1, but then the other cases are going to be opposite depending on which situation we're dealing with. Now for both of these, the 1 in the integral, so like the integral from 0 to 1 or 1 to infinity, that 1 can be replaced with any finite number bigger than 0. And it'll still be the same. It'll converge and diverge in all of those cases regardless of what that 1 is replaced with. So we could have the integral from 0 to 7 and then the integral from 7 to infinity. Those are still the same cases. We also have the comparison theorem. So if f of x and g of x are both continuous functions, with f always greater than or equal to g and both of them are always positive, then the integral from a to infinity of f is convergent. So if the integral from a to infinity of f is convergent, then the integral from a to infinity of g is also convergent. And if the integral from a to infinity of g is divergent, then the integral from a to infinity of f is divergent. So that's basically going to be the same thing in all of our cases. It's just our bounds are going to be different. So this one is the integral from constant to infinity. The same thing would happen from the integral from negative infinity to a constant. It's the same situation. If f is convergent, then g is also going to be convergent, or if g is divergent, then f is divergent. And then the same thing will happen if we have discontinuities, where f is always greater than or equal to g, with possible exceptions at discontinuities. So it might be possible for g to be bigger than f, but only at the discontinuous points. That's the only place where we are allowing g to be bigger than f. But if that's the case, then if f is convergent, then g is convergent, or if g is divergent, then f is divergent. It's the same situation in all of these. It's just a matter of our bounds that is going to be changing. I hope this video was helpful. Please check out some of my others, and please like and subscribe so you don't miss any of my future videos. Have a great day, and good luck with the rest of your math.